All right, so welcome back everyone to your Comp 335 tutorial. So in this tutorial, we'll be doing a quick review of closure properties and regular expressions. Then we'll be looking at how to convert an arbitrary finite automata to a regular expression. We'll look at an introduction to grammars, and we'll end off with using closure properties to prove that a language is not regular. Okay? So let's get started with the review. As always, I encourage you to pause the video and try these exercises on your own, and we'll go over the solutions in a few seconds. All right. So for exercise 1, we had a true-false, where the question was claiming that if L1 different L2 was finite and L2 was regular, then this implied that L1 is regular. And so this is an example of sort of using the converse of a closure property. And typically the converse of a closure property is going to be not true. And so it is indeed, in this case, false. I'm going to show you a counterexample for why that is. Okay, so we want L1 minus L2 to be finite, and we want L2 to be regular. So one thing we could do is we could say, let's pick L2 to be the universal set, or sigma star, the set of all strings. Okay, and then we know that for any language L1, where you do L1 different L2, then this is always going to be the empty set. Okay, why? Because let L1 be an arbitrary language. L2 is the set of all strings, so you're removing from L1 all of its elements. So if you remove all of the elements from a set, you get the empty set. Okay. So now let's see if the conditions in the if statement are true. So L2 is sigma star. This is regular, so that holds. And L1 minus L2 is the empty set. This is finite because it has 0 elements, because the empty set has no elements. And so this also actually implies, even though it wasn't asked in the question, that L1 different L2 is regular. Okay. So now we have shown true conditions for the if statement. Now what we want to do is, to disprove this, we want to find an example where L1 is not regular. And so we can do that quite easily, because remember, L1 can be any language, because if you take any language different sigma star, it's going to give you the empty set. So I could, for instance, pick L1 equals AN BN, where n greater or equal to 0, and this is not regular. So again, you still don't know why this is not regular. You'll very most likely see this in tonight's lecture. But L1 is not regular in this case, and so this is a counterexample that disproves the claim in the first question here. Okay, so for the second question, we had the claim that an FA can always be changed to have a single final state. So this was kind of a trick question, because here I had said FA. So an FA is either an NFA or a DFA. So in fact, if it was only an NFA, then it would have been true. Why? Because take any NFA, so it starts with an initial state. Then let's just make a box, a big box for the NFA. It has a bunch of non-final states, and let's say it has a couple of final states. Then we can always convert this NFA, let's call it M, to a new NFA M prime, so to a new NFA M prime with a single final state by doing the following. So we make this guy non-final. So we make this guy non-final, and we make this guy non-final, and we lambda connect both of them to a single final state, because lambda transitions are allowed in NFAs. Okay, so that's why this is true for NFAs, but for DFAs, this is not always true. Okay, for instance, if I give you the following DFA, so I have my initial state, I see an A, I go to a final state, see anything else, I go to a trap state. Okay, and then if I see a B, I go to a final state. If you're in that final state, you go back to yourself when you see a B. If you see an A, you go back to the initial state. Okay, so I needed to use a bit of a complicated example to show this was not true, and you'll see in a second why. So first of all, we can't do the trick where we use lambda transitions. Okay, this is not allowed because a DFA does not allow lambda transitions. Okay, it's fully deterministic. Okay, so that option is removed. The other thing you might be thinking of is maybe this DFA, can we always minimize? So can we always minimize this DFA to get a single final state? Okay, and in fact, in this example, we can see that there is no such minimization where these two final states merge. And that's because if you're in this final state, if you see an A or a B, you go to a non-final state. So that's one partition. But if you're in this final state and you see a B, you're going to go in a partition with final states. So we can see that for B, the final states go to different partitions, and so you can't do this minimization where you would merge the two final states. And so this is a DFA where you cannot change the DFA into another equivalent DFA that has a single final state. So that's why this claim is false. Okay. The next one we had, we wanted to know if the following regular expressions were equivalent. So remember, this is just the symbol for equivalent. And we didn't really go over the equivalency in the tutorial. I posted an additional recording for it. But as a reminder, if you have R1 equivalent to R2, this is true if and only if the language denoted by R1 is equal to the language denoted by R2. Okay, so if this is true, then you would need to show that the language denoted by the left-hand side is the same as the one denoted by the right-hand side. But if we pick a very basic example, like let's say R1 is A and R2 is B, then we would need to show that L of AB star is equal to L of BA star. And I think you can already see that this is not true, but maybe just as a refresher of converting a regular expression to a language, this guy here, L of AB star, so on the left-hand side, this is equivalent to L of AB and all of that star. And then this is equivalent to AB star. So that's any number of A's followed in a string, basically. Whereas on the right-hand side, you have BA star. And so we can clearly see that these two languages are not the same because namely, this guy is going to start with an A and this guy is going to start with a B for any string except lambda. So we have that LR1 is not equal to LR2, which means that R1 is not equivalent to R2. So that means this statement is false. Okay. And the last one here is we wanted to create an FA that accepted the following language. So we had a language denoted by a regular expression intersect another language denoted by a regular expression. Okay. So this might have seemed complicated at first, but if you had started to write a couple of the strings in each language, you would have seen a sort of pattern. So let's do that. We have BB as the shortest string in this guy. Then we have AB, BB. then A, B, 2, B, and so on. Okay, and then for L of B, B star A star B, then what's the shortest string? It's going to be when you have this zero number of times. So you have BB. And then after that, you're going to get strings that look like B, and then maybe a bunch of B's, then an A, and then another bunch of B's, and then an A, and then it ends with B. So we see that, in fact, the only strings that these two languages have in common are BB and BB. And to justify that, that's just because all of the strings in this guy, except for BB, are going to start with an A, and all of the strings in this guy are going to start with a B. So clearly, the intersection can't contain any of these guys, because none of the strings in here start with A, and vice versa. And so this is the only common string. So then this just reduces to the language BB, and then we can easily create an NFA that accepts this as just you read a B and then another B, and then you go to a final state. Anything else is going to be rejected. Okay, so that's an NFA that accepts the language. All right, so that's it for the sort of review. Now let's switch gears to converting FAs to regular expressions. So to convert an FA to a regular expression, we use the notion of a generalized transition graph. And this is just a very fancy word to say that it's a transition graph where the edges can now be labeled with regular expressions. Okay, so other than that, it's the same as any other transition graph. It's the same as any other graph for an NFA or a DFA. Okay, so the reason why we use general transition graphs is they allow to very easily map the graphs to regular expressions. Okay, so what do I mean by that? Well, if we take this transition graph, or this general transition graph as an example, and we want to know what the language accepted by this GTG is, using regular expressions, so using regular expression notation, well, we can see that you're going to start at Q0, and then from Q0 you can read any number of A's. So your language is going to be L of any number of A's, and then it can either read a BA or an A. So then the language denoted by the regular expression is going to be A star, and then BA or an A. Okay, and then once you're in Q1, you either read a B or a lambda. So you either read a B or a lambda, and then you're in Q2, and if you read a bunch of A's, you stay in Q2, so you can just write A star to stay in Q2. Okay, and so we see that we can sort of, when the GTG is simple, you can easily go from the graph to a regular expression. And that's essentially the goal of the following sort of kind of algorithm, is you want to simplify your graph to get a very, very simple GTG where you can easily get the regular expression. Okay, so in the sort of broad idea, before we get into the steps, is if you're given a sort of a complicated DFA or NFA, so you're given a complicated FA, you're going to convert it to a GTG where now the edges can be regular expressions. So for instance, A comma B becomes A plus B to say A or B. Okay, so you do that conversion to get edges that look like regular expressions, and then you want to essentially simplify the GTG to get a transition graph that looks like this. So this is your goal. So this is your goal. Okay, the goal is to get a transition graph that looks like this, where you have one initial state and one final state. Okay, and nothing else. So why does this make writing a regular expression easy? Well, if you have a graph like this, then it's kind of easy to see what the regular expression that denotes the language accepted by this graph is. And that's just going to be, so you're going to start in your initial state Qi. And then here the notation is the edge is labeled with R. So let's say you have a state Qi and a state Qj. The edge from Qi to Uj is going to be labeled Rij because it starts at I and it ends at J. Okay, so that's the idea behind the notation. So that's why in this case we have an edge that's labeled II because Qi starts at I and then it ends at I. Okay, so you have a self loop on Qi that's labeled Rii. That's a regular expression. So remember, these are all now regular expressions. Okay. And then you have an edge to Qj, an edge back to Qi, and a self loop on Qj. And now you can sort of translate this to a regular expression by saying you start in Qi and you read any number of Rii. So that's why here you have Rii star. Then you go from Qi to Qj. So you read an Rij. And then once you're in Qij, you could stop, or you could loop on Rjj a bunch of times. Or the other situation, the other case is you're in Qj and then you go back to Qi with Rji, then you self loop with Rii, and then you go back to Qj with Rij, and that's denoted here. So j to I to I any number of times, and then I to j. And then all of this, so you can sort of interchange the order of going back to Qi and going to Qi and back to Qj, and then self-looping. Okay. Okay. Oh, sorry about that. And then self-looping back to Qj. Okay, so you can interchange that order. So that's why we have Rjj and this other regular expression, whole star. So again, that's just because you can interchange the order of if you loop back to yourself, or if you go back to Qi and then again back to Qj. Okay. So the idea again is to get a general transition graph that looks like this. Okay. Sometimes it's possible that, for instance, this guy is missing. If that guy is missing, then you would just, for instance, remove this regular expression. Okay. So the book uses the notation of sort of an empty set, but I found that a bit confusing. So if that edge isn't there, you just don't include it in the regular expression. Okay. All right. So now the actual steps. So you're given an FA and you want to convert it to a regular expression. So the first thing you need to do is you need to make sure that your FA has a single final state. Okay. And so if that is the case, then you can move on. Otherwise, then you need to do what I sort of showed in exercise 2, where let's say you have 2 final states. Okay. Then you need to create lambda transitions to one single final state, and then these become non-final. Okay, so you need to do that, otherwise you can't get this sort of simple general transition graph. Okay, so then you get a bunch of cases now. If after doing that, after getting a single final state, you only have an initial and a final state, then so you have something that looks like this, then you can directly convert it to the formula we just saw, with the sort of self-looping at Qi and then going to Qj and back and forth. Okay, so that's the best case scenario. That's if you have already a single final and a single initial state. Okay, and nothing else basically. Then it gets a bit more complicated. So now, what if you have 3 states? So you have your initial state Qi, your single final state Qj, and then an intermediate state Qk. Okay, so here the intermediate state is Qk, and we label the edges similar to the convention seen before. So if you're in Qi and you go to Qk, then you label that Rik. Okay, So that's the idea behind the notation. And so what you need to do now is you want to remove QK, and to be able to do that, to be able to remove this guy, you need to conserve all of the transitions that go through QK. So what you're going to do is you're going to find all of the transitions that go through QK and then place them in this new graph, which has the smaller number of states. Okay, so you essentially transfer the transitions to the edges in your new transition graph. Okay, and then you're essentially conserving all the possible paths. So then you're allowed to eliminate QK. Okay, so for instance, I'll go. So I'm going a bit fast on sort of the abstract because it's clearer when you see an actual example. But for instance, one of the possible paths that QK contributes is if you're in QI and you want to go to QJ, you can either go directly with our IJ. Okay, so in this simplified graph, you conserve this Rij here, or there's actually another option. If you're in QI, then you can take QK instead of going directly. So you go from QI to QK using RIK, and then you can stay in QK a couple of times with RKK, and then from QK, you can go to, from QK, you can go to RJ, or sorry, from QK, you can go to QJ with the RKJ edge, okay? So in other words, that means that not only is there a direct path from QI to QJ, there's also this intermediate path where you go from I to K, and then you stay in K any number of times, and then you go from K to J. And then the same idea repeats for if you want to stay in QI, if you want to stay in QJ, or if you want to go from QJ back to QI. Okay, so in this case, these are all the possibilities that this intermediate state contributes to. Okay, so then that's if you have 3 states. If you have more than 3 states, you essentially pick an intermediate state. So you could have a couple of intermediate states, and you essentially repeat the process on each intermediate state. So maybe this intermediate state allows you to go from here to here. So then when you delete this guy, you take the regular expression R1 and the regular expression R2, and you add it to, you create an edge R1, R2 that allows you to go directly from here to here without this intermediate state. Okay? And you basically repeat this process until you only have an initial and final state. And then once you're there, then you can apply that formula that we just saw where you have an initial and final state. Okay, so this again might seem a bit abstract. That's why we're going to look at an example. So suppose you have the following FA and you want to convert it to a regular expression. So the first thing you want to do is, this is an FA, you want to convert it to a general transition graph, meaning that all the edges are now regular expressions. So you don't really need to change much except for this guy. From 1 to 2, you have the label A comma B. Instead, you can write this as A or B with a plus in terms of regular expressions. Okay? And that's what we're going to do here. The other step would be to get one final state. But in this case, we have a single final state here. Okay, so we don't need to do anything else in the meantime, basically. Right? So now now that we have our single final state and we have our general transition graph, we want to start eliminating intermediate states. Okay. So in this case, you need to eliminate 4 and 2. It doesn't matter in what order you do it. It'll change the look of your regular expression, but they'll be equivalent. Okay. So let's say, just for the sake of it, we start with 2. Okay. So I want to be able to remove 2 at the end of this process. So what I need to do is I need to conserve all of the transitions that go through 2. And those transitions are, if you're in 1, then you can go through 2 to get to 3. Okay, so the regular expression that denotes that basically is you go from 1 to 2 with A or B, and then you stay in 2 any number of times with B, so you get a B star, and then from 2 you go to 3 with an A. Okay, so that's one of the transitions that 2 allows you to make. The other one is if you're in 4, you can go to 3 by taking 2. And to do that, you just look, you're in 4, you see a B, and then you see any number of B's, so you get a B star here, and then you see an A and you get to 3. So if we now want to remove 2, then we need to conserve these transitions. So that's what we're going to do. We're going to eliminate the state here, eliminate the edges that are incident with this vertex, and then create sort of direct connections. So from 1 to 3, you're going to get A or B, and then B star A. And then from 4 to 3, you're going to get the direct connection B star A. And that's what we have here. Okay. So basically now I've been sort of allowed to remove 2, making my transition graph a bit simpler. Okay. Now again, we're not done because we still have 4 as our intermediate state. And so we're going to remove 4 as well. So to remove 4, you need to conserve the transitions that it allows you to make. So in this case, the only transition it allows you to make is if you're in 1, instead of going directly to 3 with this edge, you can take sort of 4 to go. So you can take, you can go from 1 to 4 seeing a B. And then from 4 to 3, you can take this regular expression. So that's why from 1 to 3, now we have 2 options. We have the original edge, and then the second transition that was allowed to exist thanks to 4. Okay, so when we remove this state 4, okay, then we also remove all of its incident edges. And in this case, we don't need to create a new edge. We only add to the existing edge the regular expression that 4 allowed to create, okay, essentially. So now from 1 to 3, you can either take this direct path, or you can take B and then B star A, okay? And so then our transition graph becomes very simple. We have one initial state and one final state and nothing else. So now we can see what the final regular expression are. What the final regular expression R is. It's going to be to go from state 1 to 3. You can either take this regular expression or this regular expression. So the regular expression R that denotes the language accepted by the original FA is going to be this guy. And so notice in this case, I didn't have the sort of looping here, okay? But that doesn't matter. The fact that it's not there just means that you don't include it in the formula, basically, okay? So this is like a best case scenario where you have to do a little less writing, all right? So that was for that example. Now we have an exercise. So we want to find the regular expression that denotes this following language. So maybe take a few minutes to try this one, and we'll go over it together. All right, so welcome back. The idea for this exercise was, again, we wanted to find a regular expression that denoted the following language. So there's 2 ways to really do this. Either you can sort of find a regular expression directly, but that's going to be fairly complicated. The other easier way is to create a DFA or an NFA that accepts this language and then to convert it. And that's what we're going to do here. Okay, so the DFA that accepts, so I'm going to create a DFA, and the DFA that accepts this language L is going to be this one. So I'm not really going to go over how I got this because we did this in tutorial 2, but just remember that each of these states were essentially cases, and for instance, this state was the even case, and this is essentially the case that we want because the number of zeros mod 2 is 0. That means you have an even number of zeros. And the same thing for the number of ones, you have an even number of ones. So you want your strings that are accepted to end up in this this final state here. Okay. All right. So remember, before you actually start the algorithm, you need to make sure that you have a single final state. So in this case, this guy is our single final state, so that's fine. And we want to have a general transition graph where our edges are now regular expressions. In this case, there isn't a need to convert anything. So 1 is a proper regular expression, so we don't need to do anything, right? So now we can just get to converting this to a regular expression. So remember, what we need to do is we need to start by removing intermediate states to get a single initial and a single final state. In this very, very specific case, we have the single final state being also the initial final, the single final state is also the initial state. And so in this case, we don't really need to do anything different, except that we want to get this this sort of GTG, general transition graph, at the end, instead of something that looks uh, like like this. So in this case, our life is a bit simpler because it's not going to be very difficult to see what the resulting regular expression is. Okay, but just notice that this is a very very particular case. It doesn't usually happen this way, but in this case, we only want essentially we want our algorithm to give us a transition graph that looks only like this. Okay, so that's what we're going to do. We're going to start by eliminating intermediate states. In this case, 1, 2, and 3 are all intermediate states. So let's start by deleting 1. So if I want to delete 1, I need to conserve all of the transitions that 1 allows to happen. So for instance, if I'm in 0 and I want to go to 3, 1 allows that to happen by seeing a 1 from 0 to 1, and then seeing a 0 from 1 to 3. And so in this converted transition graph, if I'm in 0, then I can go directly to 3 with a 1 and then a 0. Okay. The other way it also applies. So if I'm in 3 and I want to go back to 0, I can take a 0 to 1 and then take a 1 to 0. Okay. So then to go from 3 to 0, I can read a 0 and then a 1. And now very importantly that you not forget these self loops. So if I'm in 3 and I want to go back to myself, I can go to 1 and then I can go back to 3 using this edge 0, 0. And then the same thing for the state 0, where I read 1, 1. That's going to allow me to stay at the same place. Okay, so that's one intermediate state gone. Now what I'm going to do is I'm going to remove 2. Okay, so what does 2 allow you to do? Well, if you're in state 0 and you want to go to 3, you can either take this direct path 1, 0, or you can go through 2 and go from 0 using a 0 to 2, and then from 2 using a 1 to 3. Okay, so then to go from, so this is 0, to go from 0 to 3, you can either take the direct path 1, 0, or the intermediate path 0, 1, right? And so the same idea applies the other way. If you're in 3 and you want to go back to 0, you can take a 1 through 2 and then a 0 to get to 0. So you can either take the direct path, which was 0, 1. So here there's a direct path from 2 to 0, or there's that intermediate path we just did, 1, 0. And then again, don't forget about the self loops. So if you're in 3 and you want to stay in your own state, you can either read 0, 0, or you can read a 1 twice, because you'll go to 2 and then back to 3. So you get an extra self-looping label. And then the same thing for 0. Instead, well, not instead of, but in addition to 1, 1, you also get the string, the regular expression 0, 0 to stay in your own state. Okay. And then finally, this is my last intermediate state. The only thing this intermediate state 3 allows you to do is if you're in 0 and you want to stay in your own state, then you can go to 3 by reading either 1, 0 or 0, 1. Then you can stay in 3 a bunch of times. So you can stay in 3 a bunch of times here. So that's why this guy here is 0, 0 or 1, 1 star. And then from 3, you can go back to 0 with 0, 1 or 1, 0. So then in addition to the original edges on the state 0, 0, 0 or 1, 1, you also add this, this regular expression that corresponds to a transition that was allowed thanks to this intermediate state. Okay, so now you're almost done, but it's almost clear what the regular expression should be. If you start in this initial state, then you can read any of these guys and any combination of these guys any number of times, and you'll stay in your final state, meaning that the regular expression is just 0, 0 or 1, 1, or this big boy here, 0, 1, 1 star, 0, 1, 0, whole star. Okay? And then this becomes the regular expression that denotes the language accepted by this DFA, or denotes the language which is represented in set builder notation here. Okay, and that's essentially, so with this sort of idea of intermediate states, that's how you reduce your general transition graph to get some final regular expression. All right, so for grammars, let's start with a very gentle introduction. So a very formal sort of definition. A grammar is a 4-tuple G, where you have 4 components in this tuple. You have V, which is a set of variables, T, which is a set of terminals, also lowercase symbols. Typically, these are the same as symbols in your alphabet. S is the unique starting variable, and P is a set of production rules. Okay, and a very important thing to note is that your production rules will always have the form X right arrow Y, or just X derives Y, X gives you Y, where X belongs to essentially any combination of terminals and variables with this plus operator, and Y is any combination of terminals and variables with a star operator. So the only thing that you sort of need to be careful so far here is to note that, for instance, A, let's say this is a variable, gives you a lambda. This is a valid production rule, but lambda gives you A is not. Okay, and that's because this guy is a plus, and in this case, we assume that both the terminal and the terminal set and the variable set do not contain lambda. So then this operation here is not going to give you the empty string. Okay, so for example, we have the following grammar where we have 3 variables, and typically the start state is always denoted by S. Our terminals are A and B, so you can also think of this as just the alphabet. And then we have our production rules listed sort of in this following manner. This bar here, where you have S gives you A bar lambda, this is just short form for saying that S gives you A and S gives you lambda. So it's sort of to make everything sort of more compact. Okay, but these two notations are equivalent. No better, no worse than the other. Okay. So what does a grammar do? A grammar essentially derives strings, and a derivation where we say that y can be obtained from x is denoted as x right arrow y, or you can just say that x derives y. Okay, and essentially that just means that you start at x, and through a series of rules, you can get to y. Okay, so for example, from the previous grammar, we had the following production rules, and the grammar G could generate a string, for instance, BBBA. Okay, so we say the grammar generates a string if there is a set of production rules, if there is sort of a sequence of production rules that starts at S and that gets you to that string BBBA. So in this case, you can start at S, okay, and then you can apply the first production rule, S gives you A. So really what you're just doing is wherever you see an S on the left-hand side, you replace it by an A. So then S just converts, or S derives to A, okay? And then from A, you use the production rule that A gives you BB, capital B, A. So then you say that A derives this expression, okay? And so now I have a variable B, okay? This variable B, what I'm going to do to derive this string here is I'm going to apply the production rule B gives me, capital B gives me small b, okay? So essentially, instead of a big B here, on the right-hand side, I'm going to replace it with a small b, and so that's what I get here. I'm done with my production rules because now I've reached a string. So now this is a string over the set, over all the possible strings from the terminal set, the set of symbols in the terminals. Sorry, that didn't make any sense. I'm done here because my string is composed of symbols only from my set of symbols T. So in other words, this string B is in T star, any string that can be formed from the symbols in T. Okay, that was a bit better. So instead of writing this whole sort of derivation, what you could also say is S through 0 or more steps gives you BBBA, okay? And so a grammar in general, what it does is it generates a language, and the language generated by G is essentially a set. It's a set of strings. The strings are formed from symbols in the set of terminals, okay, where all of those strings W, can be derived from S with a set of production rules, okay? So for example, in the grammar we've seen so far, we have these production rules, and we want to know what are the possible strings that can be generated from the grammar G, or in other words, what language does G generate? Okay. So to find this, we essentially need to find a pattern or list all of the production rules that start at S and that end with only symbols. So that's a very important concept to understand. Your production rule, so for instance, this production rule produces a string that is part of the language only if at the end you only have symbols, you only have terminals, and you don't have any variables. So for example, it's true that S gives you A, but this capital A is not going to be part of my language L of G, and that's because capital A is a variable, okay? So what do we need to do to find the language generated by G? We need to list all of the strings generated from the grammar G starting from S, okay? So if I'm in S, right, I start my variable always starts at S. then I can use the very simple production rule S gives you lambda to get S gives you lambda. So now lambda is part of L of G, the language generated by G. What I could also do is I see an S, then I go to A. So I use the production rule S gives me A, and then A gives me the string, the symbol A, because I can use the first production rule, A gives you A. Okay? So then the symbol A is going to be part of L of G. And then again, the same thing, except that you go from S to A, and then from A, instead of using the first production rule, you use the second one, where you get BB capital BA. And then you have a variable here that you can either replace with B or with lambda. So in this case, I replaced B with lambda, and in this case, I replaced B with little b. And so I get the next two strings in L of G, and these are in fact the only possible strings that can be derived from this grammar. Okay? So that's the first example with G generating a language. So we have another example here of a different, oh, there's a typo here, okay, of a different grammar over the, so the grammar contains two variables, S, capital S, and capital B, contains the terminals AB, the start variable as usual is S, and this is the production rule. Okay? So we want to know what are the strings generated by the grammar, or in other words, what is the language generated by the following grammar. So we essentially need to start from S and then try to see all of the possible derivations that can result from S to get only strings that contain terminals. Right? That's the key here, only terminals at the end. So you can use, starting from S, you can use the very simple production rule, S gives you lambda, and then at that point you can't sort of keep going because lambda is not a variable. It can't give you any new sort of symbols. Okay. So I have so that means that a string that's part of L of G is going to be my empty string. And then another possible derivation is if you start at S, you can use the derivation S gives you capital B little b. So you get capital B little b. And then you can essentially, you have many cases. You can either replace B with this guy or replace B with this guy. And you can sort of apply that concept any number of times. So in this case, I see a B, and I'm going to use this production rule, B gives me lambda, to only get B. Okay. Or what I could have done is I see a B, and I use the first production rule, and I get two B's followed by another variable B. And then I see another variable B here. I can either replace it with lambda or again with this guy. In this case, I replace it with lambda, but now in this other case, I replace it with BBB. So maybe this is an important thing to notice. Here, your B here is replaced by BBB because you're using the production B, BBB. Really, you can think of this as the left-hand side is replaced by the right-hand side, okay? And so what you can notice is all of the terminals, all of the end derivations contain strings over terminals B, where the length of that string is odd. Okay, so in this case you can get a single B. In this case you get 3, but in general you can get any odd number of B's, of consecutive B's. And so that's why in general you can say that S derives B and then BB star. So this is just the regular expression that denotes the language of strings over B, where the strings have an odd length. Okay, so that means that the language generated by G includes lambda, and it also includes B to the 2n plus 1. So this just means that you have an odd number of a consecutive number of B's where the number of b's is odd. Okay. So this is the language generated by G. And so you needed to sort of convince yourself by doing a couple of examples and then seeing that there was a pattern in the number of b's. Typically, that's what you can do to see what the language generated by the grammar is. Or you can do something a bit more complicated, which when you sort of convert it to an FA, or you'll probably see that in tonight's lecture. Okay, so another important concept is the concept or notion of linear grammars. So a grammar is either right linear, well, a linear grammar is can be right linear or left linear. Okay, so a grammar G is left linear if all of the production rules have the following form. So you have a single variable on the left-hand side, and then a single variable on the right-hand side, and then any string over the terminals. So X is any string over the terminals. Or what you could have is a single variable on the left-hand side, and then only terminals on the right-hand side. So because your variable B here is on the left, then we call this a left linear grammar. Okay. If instead of the B being on the left, the B is on the right, then that means that we have a right linear grammar. Okay. And so for a grammar to be right linear, all of the production rules have to look like that. And for a grammar to be left linear, all of the production rules have to look like that. So a very quick example of maybe a left linear grammar is just S gives you lambda, or it gives you SA. Okay, so this is a left linear grammar. The sort of equivalent grammar in sort of right linear terms, so a right linear grammar would be S gives you lambda or AS. Because your variable, you have a single variable on each side, and your variable on the right-hand side is to the right of the terminal. Okay? And so we say that a grammar G is regular if it is either right linear or left linear. So for example, this is a regular grammar, and this is also a regular grammar because in this case it's left linear, and in this case it's right linear. Okay? So a more concrete example, we have the following grammar here, and we see that it's in fact right linear because on the left-hand side you have a single variable, and then on the right-hand side you either have a terminal or strings, right? You have strings over the terminals, and then a single variable following the strings. Okay. So this is an example of a right linear grammar, which because it's right linear means that it's regular. So just sort of as an FYI, what does this grammar generate? What are the strings generated by this grammar? Well, we can actually notice that any string of the form W1, AB, W2, where both these strings are over AB, can be generated by G. In other words, any string that contains AB as a substring. Okay. To sort of illustrate this, let's look at the string BA, AB, AA. So you have a bunch of symbols over AB before, then you have the substring AB, and then a bunch of strings over AB after. Okay, that's sort of by definition, that's what a string that contains AB as a substring is like. Okay, so we can see here that you're going to start. So why does this grammar generate this kind of string? Well, you're always going to start with S. And then for the string that comes before AB, you can use the first two production rules. S gives you AS, or S gives you BS, because that essentially allows you to get any string over AB. Okay, so it allows you to get any string over AB. So that's what you're going to get. In this case, it's just BA. So S is replaced by B, then the variable S. And then you can replace your variable S with AS. So now you have BA variable S. And now you want your substring AB to occur. So you're going to use this substring AB and then shift, so sort of go to the variable A. and your variable A is going to take care of the second half of your string. So you're going to see, you're going to see BA, and then you're going to see the substring AB. And then now you have your variable A, and your variable A essentially allows you to create any string over the terminals A and B. So in this case, B is replaced by AA, and then A is replaced by, well, okay, so in this case, I'm missing a step. A is replaced by AA, and then you replace this A by lambda. So let me just, yeah. Okay, just going to make a quick note of that. Okay, so then we see that if you have any string that looks like W1, AB, W2, then that string can be generated by G. And in fact, those are the only strings that can be generated by G, because to go from S to a string over only terminals, you need to at some point get to this lambda here. Okay, and to get to that lambda, you need to go through the production rule ABA. And going through that production rule ABA guarantees that you see a substring AB in your string. Okay. So that's an example of a regular grammar. And in fact, regular grammars produce regular languages. Okay. Now an example of a non-regular grammar. So we have the following grammar here, G, where the only two production rules are S gives you ASB and S gives you lambda. And this is actually a very interesting grammar. So we can see that it's neither a right linear nor left linear, because you do have a single variable on the left-hand side, but the variable on the right-hand side doesn't look like XS, and it doesn't look like S then X. So any terminals and then the variable S, or any variable and then the terminal X, right? So that means that G is non-regular. But if a grammar has a set of production rules, it is going to produce or generate a language denoted L of G. And so what is this language here? Well, we start with the most basic production rule, S gives you lambda. Okay, so we know that L of G contains lambda, right? L of G contains lambda. Then you can use the first production rule, S gives you ASB, and then you replace S by lambda, so you get AB. And then I think you already see what the pattern is going to be here. Instead of replacing S by lambda here, you replace it by ASB. So you have the same number of A's as B's on the left and on the right. And then you can either choose to get another A on the left and another B on the right, or to stop that process and get, in this case, AABB. So really we see that S is going to allow you to derive any number of A's and any number of B's, where the number of A's is the same as the number of B's. So we get AB, A2, B2, so on. And so, in fact, the language generated by G is AN, BN for n greater or equal to 0. So here we have a non-regular grammar that produces a non-regular language, AN, BN. Okay. So now an exercise for you. We want to write a regular grammar that accepts the language L, where L contains only strings of even length. Okay, so hopefully you've had some time to think about this example or this exercise. And well, notice that what we need to do is we need to create a regular grammar. Okay, so for the grammar to be regular, it either needs to be right linear or left linear. Notice that this or is not necessarily exclusive. You could have a grammar that is both right linear and left linear. For example, well, I'm getting a bit sidetracked here, but for example, S gives you A, and then A gives you A. So if you have the grammar G here, then L of G is just going to contain the language A, is just going to contain the string A. But we see that this grammar here is both left linear and right linear, because here you have A, and then you can think of this as AX, where X is lambda, or as you can think of this as XA, where X is lambda, and then you also have a production rule that gives you a terminal. Okay. So, but that was, I sort of got a bit sidetracked there, but that's just to say that a regular language, a regular grammar, sorry, needs to be either right linear or left linear, but it's possible that it's both. Okay. So what do we need to do here? We needed to create a grammar that had an even number of a grammar that generated strings with even length. So, well, to start, you always start with your start variable s. So now, is lambda going to be in this language? Yes, so you necessarily need the production rule s gives you lambda. And then what you need to think about is, if you think about an even string, so for example, A, B, B, A, A, this is kind of similar to the regular expression notion where the string is composed of pairs of symbols, right? So when your grammar generates the string that has an even length, it generates the string by pairs. So it's first going to generate AB, then it's going to generate BA, then it's going to generate AA. Okay, and if you ensure that your grammar only generates strings like that, then for sure it's not going to give you something that looks like this, where the string has an odd length. Okay, because here to produce, it would be impossible to produce A. That's the idea. Okay, so what you want to do is you want to have your start symbol S, and then you want to produce pairs of pairs of symbols, and then keep staying at S. So then S can also produce more pairs of symbols. So for instance, if I'm at S, then I can produce the pair AA and then stay at S again. Or I could produce S gives you AB and then S, or S gives you BA and then S, or S gives you BB and then S. Okay. Or if you want to sort of make this cleaner, then you could just use these are called pipes. You could use pipes to say that it's either lambda or AAS or ABS and so on. Okay? But just like this becomes the grammar that generates all of the possible even strings over the language, the alphabet AB. And so that's it. That's the grammar for this exercise. Maybe just to make everything neat and to make everything precise, then you would need to specify that your variable set is just S, your terminal set is AB, your start variable is S, and your production rule here, you could just say this is the production rule. Okay, and that is a valid grammar, and it's most certainly regular, because here we have a single variable on the left-hand side, and then all of the variables on the right. The only variable that occurs on the right-hand side occurs after all of the strings of terminals. Okay, so that means that we have a right linear grammar, which is regular. Okay, so that's for that exercise. Finally, for for grammars, we have the notion, we have the sort of defined notion of regular grammars. What's the connection between regular grammars and regular languages? Well, you're going to see tonight that, in fact, every regular language has a regular grammar that generates it, and also that every regular grammar generates a regular language. Okay? The proof that you'll see is essentially by converting a grammar to an FA and converting an FA to a grammar. Very much how we sort of proved regular expressions. Okay, so just as a last set of exercises. We have the two following exercises. The first one is a true or false that states that there are non-regular grammars. So essentially, there are grammars that are neither right linear nor left linear that generate regular language. So this might come as a surprise, but this is in fact true. Okay, and it's actually very easy to think of an example. So you want your grammar to be not regular. So if you start at your start variable s, then s, let's say, gives you two variables, a and b. Then already this is not right linear or left linear because you have two variables. Okay, so already you have a non-regular grammar. The only thing you want this grammar to do now is to produce a regular language. And that's in fact very easy to do. Let's just say A gives you little a and B gives you little b, okay? Then if this is your grammar G, where you have, of course, a set of variables SAB, the set of terminals AB, and the start state S, and this is your production rules P, then the only string generated by G is going to be AB. And that's because if you start at S, you get AB, and then you have no choice but to replace SA with A and B with B, okay? So this is actually a finite language, which is, of course, regular, but this grammar here was non-regular, okay? So finally, what grammars generate the sort of case languages here, which are very important? So this is a bit of a trickier question. So I'm just going to write the production rules and sort of let you figure out what the variable sets are. So for sigma star, you're always going to start at S. And then essentially what you do is you want to accept lambda, okay? And then if you can also accept any other string by saying you start at your start variable S, and then you can either get AS or BS, okay? And that allows you to produce any string because any string looks like A, B, A, B, for example. So S is going to give you, first of all, A, S, so all of this is now S. And then you can sort of see how recursively you can get B, and then this is S, and A, and then this is S, and so on, okay? So this is the production rule that allows you to get sigma star. So I'm going to do lambda first because that one's easier. So if you just want to contain lambda in your generated language, then really all you need to do is S gives you lambda. Pretty easy. The last one might be a bit trickier. So you essentially don't want to produce any strings, okay? So in other words, you never want your strings, you never want your derivations to start with the variable S and to give you, so you don't want this to happen. You don't want to start at variable S and then with a finite number of steps to get a string W over T star. Okay, you don't want this to happen. Okay, so there's actually a couple of choices for what your set of productions could be. First of all, remember that P is a set. Okay, so if P is a set, you could just say that your set of production rules is empty. You have no production rules, and so the language generated by your grammar needs to use these production rules, but there are none, and so the language generated by G is the empty set. Another one that you could say is maybe S gives you S. So this is kind of a useless production rule because you start at your start variable S, and then the only thing you can do is generate S again and again and again, okay? So clearly you can never generate a string, and so in this case also L of G is empty. But really you can think of any sort of case. You could just say You can make something really complicated, like S gives you A, B, C, and then A gives you B, B gives you C, and C gives you S. It's impossible to get a string of terminals from here because clearly you see that there are no terminals at the end, right? So that means that this grammar that contains this production rule here would also generate the empty set, okay? So that's for an intro to grammars. Now we're quickly going to look at using closure properties to prove that a language is not regular. All right, so as I was saying, the last part of this tutorial is looking at how to use closure properties to prove that a language is not regular, okay? So how can we do this? Let's say you have a language L1 and you want to show that it's not regular, okay? You're going to see tonight a lemma called the pumping lemma. Well, I hope you're going to see it tonight. That's one way of showing that a language is not regular. We're not going to cover that right away. What we're going to do is we're going to try to use closure properties to show that L1 is not regular. You can't always do this. Sometimes it's necessary to use the pumping lemma, but sometimes it's actually easier to use closure properties. So to do this, we need to use a proof by contradiction. So if you don't really remember what a proof by contradiction is, basically you assume that what you're trying to prove is false, okay? So in this case, you would assume that L1 is regular, and then you need to show that this leads to some kind of contradiction, something that doesn't make sense. In the context of closure properties and regular languages, what we do is, as I said, we assume that L1 is regular. Then what we do is we try to combine L1. So for instance, maybe we can combine L1 intersect L2, where L2 is another regular language. So we assume that L1 is regular, and then we pick another regular language, L2, and we use maybe an intersection operation. And because we know that the intersection operation, that regular languages are closed under intersection, this means that L1 intersect L2 would be regular, okay? L1 intersect L2 would be regular, and we could sort of denote this as a language L, okay? So L, for whatever L is, would be regular. And the idea is to make this L, the L that we showed using this closure property is regular. The idea is for L to actually be something like AN BN, for n greater or equal to 0. Because we know that AN BN is not regular, but in this case, we're showing that it is regular, which is a contradiction. Contradiction. The symbol I like to use for contradiction is this funky symbol here. It makes your argument feel more rigorous, even when it sometimes isn't. But that's basically the idea we're going to apply. We're going to assume that L1 is at first regular. Then we're going to combine L1 with some other regular language to get, using closure properties, another regular language L. And L will need to be something like ANBN, which we know is not regular. And then that would be a contradiction, meaning that our initial assumption was incorrect and that L1 is in fact not regular. Okay, so we're going to do an example. In this case, we have the language L1, which is the set of all strings over AB, where W has the same number of A's as B's. So this might be surprising. You might tell yourself, oh no, I think I can find an FA that accepts such a language. But when you think about it, to have the same number of A's and B's, what you need to do is you need to keep track. So you need to, in some way, keep track of the number of A's and the number of B's. But an DFA or an NFA can't do that. The only thing a DFA or an NFA can tell you is what was the last symbol it read, right? Because if you have maybe an edge like this, A, then if you're in this state, the only thing you know is the last symbol you read was an A. Okay, so that's clearly not enough to find strings where the number of A's is identical to the number of B's. And so this is in fact not regular, and this proof is going to also show you that this claim is true. So again, remember we're doing closure properties and using a proof by contradiction. So the first thing we're going to do is we're going to assume that L1 is regular. Okay? So in other words, that the language that contains the same number of A's and B's is regular. It's possible to find some FA that accepts it. Okay, and so now what we're going to do is we're going to combine L1 with another regular language L2. L2 is going to be any number of A's followed by any number of B's. This we know for sure is regular because I can quickly draw a NFA that accepts it, right? This is an NFA that would accept any number of A's followed by any number of B's. Okay, so we know that L1 and L2, well, we assume that L1 was regular and we know that L2 is regular. So now what we do is we take L1 intersect L2. So what is this intersection going to look like? Well, we know from L2 that our strings have to look like, from L2, we know that our strings have to look like a bunch of A's followed by a bunch of B's. From L1 we know is all the strings that have the same number of A's as B's. So this means that the number of A's here, N, has to be equal to the number of B's here, okay? And so really the intersection of these two languages is AN, BN, okay? But now this leads to a problem because we assume that L1 was regular for the sake of contradiction, and we intersected it with L2, which we know is regular. Regular language intersect another regular language, that's going to be regular, right? So this would mean that AN, BN, for n greater or equal to 0, this guy is regular. And we know that this isn't true. Again, this is going to be shown to you with the pumping lemma, but we know this isn't true. And so this is a contradiction, okay? We have a contradiction. And so that means that our initial assumption, excuse me, our initial assumption was false, was incorrect. And so L1 is in fact not regular. And this completes the proof, right? So this still might not be super clear to you. That's why we're going to do another exercise. So we want to prove that the language AI to the A to the I, B to the J, where I are different than J, is not regular. So maybe take a couple of seconds to try to think of how you could do this by contradiction. And we'll go over a solution in a few seconds. Okay, so let's see how we can do this. So if we try to use a proof by contradiction, what we first need to do is we assume for contradiction, that L2 complement, whoops, sorry, not L2 complement, but you're going to see why I use a complement. L2 is regular. Okay, so in other words, that any number of B's followed by any number of A's followed by any number of B's, where the number of A's is different from the number of B's, is regular. So it's possible to find some kind of DFA. I don't know what it will look like, that accepts L2. Okay, so this is what the assumption for contradiction looks like. So now what I need to do is I need to use some closure properties to arrive at a contradiction. So let's say my target my target, my goal is using a certain closure property arguments is to arrive at the conclusion that an bn, n greater or equal to 0, is regular, which we know is a contradiction. So that's the goal, is to try to get to that contradiction. So how do we do that? Well, let's pick another language, L, A star, B star. So this is any number of A's followed by any number of B's. There is a regular expression that denotes it. So clearly this language, the language denoted by this regular expression, is regular. Okay, so now how can we sort of use some operations, some closure properties to get maybe an operation and then L2 to arrive at an bn. Okay, that's what you're trying to ask yourself to do this kind of proof. You want to see what operation can you apply between this guy, L A star B star, and L2 to get A and B in. Okay, so it turns out that if you do the following operation, so if you complement L2, okay, and you take L2 complement intersect L A star B star, then you're going to get AN. So it might not be super clear why, so I'm going to do an aside and show you why exactly that's true. So remember, L2 is all of these strings where there's a bunch of A's and then a bunch of B's, and the number of A's is different from the number of B's. So that means the complement of L2 is, first of all, going to have a bunch of A's, a bunch of B's, where the A's and the B's are the same number. So L2 is going to have AN, BN, such that n is greater or equal to 0. And it's also going to have some other strings W, okay? Some other strings W, where, if you'll remember your assignment 1, where BA is a substring of W. So W over AB star. Okay, this is what the complement is going to look like. And so the complement is clearly not regular actually, but for the sake of this exercise, we assume that L2 was regular. So if L2 is regular, and then you take the complement of a regular language, you also get a regular language. Okay, so that means that this guy is regular. And so now remember, what you're doing is you're taking L A star B star and you're intersecting it with L2 bar, L2 complement. So from this guy, we know that our strings are going to have a bunch of A's followed by a bunch of B's. And then from this guy, we certainly can't sort of include the strings that have BA as a substring, because that's not in this language here. So that would sort of not hold with the intersection operation. So really, the intersection is going to just lead to AN BN, because if you want to think of it, L2 bar is for certain strings going to have any number of A's and then any number of B's, where the number of A's is the same as the number of B's. And it has, well, sorry, L2 complement is those number of A's and those number of B's are different, okay? When you complement that, then you get those number of A's are the same as those number of B's, and you're intersecting it with strings that start with A's and then finish with B's. So sort of you can see that the intersection is going to give you AN, BN, okay? And so remember what we did now, we have L2 complement is regular, L A star B star is regular, and the intersection of two regular languages is also regular. So this means that AN, BN is regular, and this is a contradiction. So that's my symbol for contradiction. So That means that the initial statement, can't spell statement was false, meaning our assumption, our initial statement was incorrect, was false. And so that implies that L2 is not regular. Because otherwise, if it was, then it would lead to a contradiction. And that sort of finishes that proof. Okay. And so that's it for this tutorial. Thanks for listening. And I hope this was helpful. All right. See you.